Okay, welcome to video 2. You may recall last time we talked about reflection and about flat mirrors a little bit. Now we're going to take a look at a little bit more interesting curved mirrors. In AP physics, we can describe the mirrors by shape and also by process. So I'm going to start by talking about by shape. If you think about, and you've probably heard this before, but we take a look at two different types of mirrors. We have concave mirrors, and these are from a side view. The mirror is curved, so it curves inward. So the mirror has a reflective surface on the front, that's this side. And the back, because the mirror, light doesn't go through a mirror, we don't care about what's happening on the back, so here I've drawn it as a flat mirror. So light comes in this way, strikes the mirror, and then the light's going to bounce off, but it's going to bounce off in a different direction, still obeying the law of reflection, because it has to be a law that the angle of incidence, angle of reflection are the same. But a concave mirror is also known as a converging mirror, and we'll talk about that again a little bit later. But the shape is going to be curved inward. A convex mirror does the opposite. We have a line defined as principal axis. We'll talk about that later. And here the mirror curves outward. So light ray coming in, hits the mirror, bounces off, and goes off in this direction. You've probably seen both these. If you think about a spoon, for example, if you pick up a spoon at dinner and look at one side, if it's curved inward, then we have a concave side of the spoon, the part that you pick up the soup with, and if you flip it over to the other side, we have convex. So mirrors are classified one way by their shapes, concave and convex. Now this is a really important picture. We're going to define the parts of a concave mirror and the key points from which we do what we call our ray diagrams. All of the mirrors and lenses we're going to take a look in our unit on optics are all spherical. So they're all spherical in nature, meaning they're parts of a larger sphere. So here we have a curved mirror, and I chose to show you concave because it's the more common. What you have to remember is that this is really part of a larger spherical surface. So we're actually taking a look at this thing going all the way around in a giant circle. And that's important because we're going to define some points relative to that. The first point we're going to take a look at is something called the center of curvature, and this is literally the center of the circle from which around this mirror is drawn. So somewhere over here I have the center of the mirror. The distance from the center along this line, which is known as the principal axis, we have a point over here called the vertex. And the distance from the center to the vertex is the radius. It's the radius of the circle. At a point exactly halfway between the center of curvature and the vertex is someplace called the focus. And I'm sure you've heard about the focus point of a camera or a lens or something. But here we have the focus or the focal point. And so again, and it turns out because CF is a distance, it turns out that CF is exactly half of CV. So in other words, this segment right here and this segment right here are the exact same length. Or in other words, F is exactly in between C and V. And that's only because it's spherical. So these are kind of some key points that we're going to use for our ray diagrams. Now, these are the rules for drawing ray diagrams. So this is going to explain to us why images form, where they do, and with the properties that they form. So again, what I've done here is I've listed the 3 rules for drawing ray diagrams. I've also, again, picked a concave mirror, a mirror that curves inward. Most of our cases are concave, so I'm picking that. This out here is the object. So we have some object. It could be a person, for example, standing in front of a concave mirror. So we define this as the object. What I'm going to do is that rather than taking this object, of course, is made up of thousands of individual points, or actually an infinite number of points. What I'm going to do is I'm going to take the point at the very top. And I'm going to follow the rules to figure out where the image forms. So, for example, let's say here's my curved mirror. Here's my vertex over here in this point. I'm going to pick a point over here and call this the focus. And out here someplace, and I'm just doing one example, this might be the point C. So the focus is a certain distance out from the mirror, and the C is twice that distance. The first rule says if I take a point and I shine a light ray from that point, so I'm going to take this point right here, shine a light ray from that point, and I bring it in parallel to the principal axis, parallel to this lower line. The light ray is going to come in parallel, and the rule says the light ray has to hit the mirror and reflect down to the focus. So it has to do that. Now that's actually doing this, and you don't really need to know this, but I'd like to show it. It's actually doing this because if you think about this curved mirror, this mirror is spherical. This point, because C is the radius point, any line drawn along this is going to hit that mirror at a right angle. if you think of this as a tangent line, and here's a normal line coming out from C, it's going to hit at a right angle. So if you look at this, this goes back to our earlier study. Light ray comes in at an angle of incidence. It's going to strike the mirror. It's going to reflect out at the angle of reflection. Because these distances are halfway, these angles are halfway. So it's really, the first rule is really a consequence of the law of reflection. Now again, you don't need to know that, but I'm just trying to show you where it came from. These rules come from someplace. They're not arbitrary rules that were passed down by God. Well, maybe they were, but it's up to you. So here we have a way of looking at the rules. So light ray coming in parallel comes out through F. That's our first rule. The second rule is simply the exact same statement, but in reverse. Well, if a light ray coming in parallel goes out through F, a light ray down through F has got to come out parallel. So again, and because these are light rays, we put arrows on them, kind of like vectors. I usually show one arrow on the way in and one arrow on the way out. Now, these, again, the light ray came in parallel, passed through F, came down through F, passed out parallel. These light rays are going to meet right here. So these light rays are going to converge at this point. Well, if this was a point we called A, and the light rays bounced off the mirror and came to this point, we'll call it A prime. We say A prime is the image of A. Now, rather than doing this for every single point in this object, we're simply going to use the logical conclusion that if a point A forms an image right here, A prime, every point underneath of A will form an image underneath of A prime. So what happens is you actually form an image at this location. And you'll see this in the lab. You may have experienced before. If you looked in a mirror, you see an image that's upside down and appears smaller. So here's an object. We follow the light ray rules, and we get an image down here. Now there is a third rule that sometimes is handy. And the third rule says if I send a light ray towards the mirror along a line joining C in the object, it will bounce off the mirror and come straight back. So if I send a light ray down through C, it will hit the mirror. And again, because C is a normal line, the light ray is going to come right back out through C. And it turns out that also works. So if I send a light ray in from A down through C, it also passes through the exact point, and it has to. All three rules have to work. It's going to hit the mirror, again, along a normal line, come right back out. And so all three of those points will hit at the same location. So we use these three rules, in parallel out through F, into F out parallel, and in through C back out through C. We use these, any two of the three, to form an image with a curved mirror. The lab that you're going to do is going to let you practice that. Now we also have some vocabulary, and we use the hi-ho, di-do vocabulary. If I place an object, for example right here, this distance of the object to the vertex is do. It's how far the object is from the mirror. If I form an image down here like we just saw, this distance would be di. It's how far away the image is. All of these are relative to the vertex. So it's the distance from the object or the distance from the image to the vertex. We also can talk about the height of the object, ho, and the height of the image, hi. So we come up with an equation, we'll talk about a little bit later, it talks about hi, ho, di, do. There's a ratio. The ratio of this height to this distance is the same as the ratio of this height to this distance. So it makes for a very convenient mathematical expression that is very useful. Again, you should now try with pencil, use the rules I gave you, try to do the sheets that are downloadable as the Curve Mirror Lab. Try to form the image using any two of the three rules. Some of them are a little tricky. We'll go over them a little bit later. And try to label, find the image labeled A prime as opposed to A. Now, there is an answer key. The second document that you download off my webpage actually shows you the correct answers drawn professionally. And the cases that are trickiest are 5, 6, and 7. So the first three are pretty good, but 5, 6, and 7 are the trickiest. And again, you have the answer key. When you're doing the lab, try to pay attention. Are the images real or virtual? Are they upright, inverted? Are they larger, smaller, or the same size? So there's a space on that lab on the far right to fill that in, and we will talk about that. I really want to emphasize that if you do this really carefully on this lab and understand it, it turns out the lens analogy, the lens cases that we'll take a look at in the next chapter are almost identical. So if you get it for mirrors, it will make a lot more sense for lenses. Okay, and again, we'll talk about these cases a little bit later. As I mentioned before, sometimes you use different vocabulary. Sometimes converging means the light rays come together. So pay attention. I think you'll see that a concave mirror is also a converging mirror, and a convex mirror is a diverging mirror. So if you look at your key, you can see this. Now the last thing I want to do is give you the mathematics for this, and I'm just going to give you the equations. The equation for relating the focal length of di into do is written as 1 over f equals 1 over di plus 1 over do. That's something you can confirm in the laboratory, but I usually just tell people that's the equation. Just be careful. You can't flip it over. You can't say f equals di plus do. It's kind of like resistors in parallel. The other thing you can do is if you're solving for f, use the equation in this form. So if you're solving for f, just use the, again, similar to the resistor in parallel equation. If you're solving for di or do, you can do the same thing. I usually rewrite it as di equals f do. I'm basically doing the algebra for you, and do minus f. And of course, if di equals that, then do must be the opposite of that. Just substitute the letters back the other way. So normally what's happening is we're going to give you do and f, and you solve for di. So this is the most common use of the equation. The other equation I just mentioned was one that says high over ho equals di over do. And this is also, if you take the absolute value, it's also called magnification. If I take a look at how big the image is compared to the object, we call this magnification. And we usually express it as an absolute value. Now, there are some sign rules, and I'll tell you right now over here, the sign rules I do are different than some other books and some other teachers. Half the people do it one way, half the people do it the other way. It doesn't matter if you do it the way of the book or the way I do it. I treat it the following way. If anything is behind a mirror, so if anything occurs behind the mirror, mirror should bounce things off. So if something happens behind the mirror, it's negative. So that could be the height of the image, the location of the image, the DI, the HI, or if you even use the focus behind the mirror, which sounds strange, but we'll talk about that a little bit later. So anything happening behind the mirror is negative, and obviously anything in front of the mirror is positive. And I'll show you an example or two. Again, you can stop this and take a little break, but I'll show you an example or two of how you do this. The first thing I really want to stress to you is if you know the cases, it's really easy. So when we're doing problems, I usually sketch a picture, I think about the case, and then I go ahead and do the math. So here we say we have a concave mirror. So I'm going to draw a concave mirror. It says the focal length is 7. I come out here someplace and I say f equals 7. If a 5 centimeter high object is placed 20 centimeters, well, I try to think about this. I say, well, if that's f, then 2f, or c, must be at 14, and my object's out here at 20, so I say do equals 20. Now it's simply saying, well, I'm looking for the location of the image. I'm looking for di, so di must equal f do, do minus f. So I'm going to plug in numbers. I'm going to say 7 times 20, and then my do will be 20 minus 7, so I'll get 140 all over 13. And that's going to be a little bit more than 10. If you look at the picture, again, you could sketch this out and actually do this, but in parallel down through F, out parallel, this image will form somewhere there, and the number you get should jive with the picture you get, so it should make sense. You can do the same thing for the height of the image. We can say high equals ho di over do, and these are just plug and chug. We have to give you 3 of the 4. You plug numbers in, out comes the answer, and it should jive with the case. If you look at this, I would call this case 2 from the lab you just did, because the object is outside of 2F or C. So again, once you get acquainted with the cases, it becomes pretty easy. There are other examples. You might want to pause the video, do this example, see if it makes sense, and check your answer with the answer key. Likewise, in example 3, they can get trickier, so just be careful. Likewise, you might want to pause the video, do the calculation, see if it makes sense, and check your answer with the key from the lab, and see if you have the right case. There is a homework set with answers that you can practice this with. And again, this is the key. If you learn the cases well, then life becomes easy. It's kind of like Doppler. You'll know the answer before you hit the calculator buttons. That makes life nice. I do have a calculator program that does this. It's called Lens Mirror. It actually does all the calculations for you. You can have a copy. But do the homework set, look at the answers, see if they make sense, and then if you have questions, come see me. Okay, it was a little bit long, I apologize, but I think you'll find that helpful.